The bio on David's poster, but he was a PhD student of Bjorn Poonen from UC Berkeley. He then spent a year at Wisconsin as a postdoc with Jordan Ellenberg, and then moved to Emory University. And he has been at Amherst College since 2023, correct? Yeah. Some things you might not know about David. So David was my PhD advisor. I took the very first class that David taught at Emory University in fall 2011, Math 250, a proofwriting class. So David has known me since I could prove that the sum of two even numbers was even. And yeah, so he taught me how to do that. I spent 10 years at Emory as an undergrad, master's student, and PhD student. David started mentoring me as an undergrad and continued through PhD. So I've known David for a long time. He's a great friend. He was the best man at our wedding. So also fun facts, David is an avid fan of metal and an avid Magic the Gathering player. So if you have any interest in these things, I'm sure David would love to talk to you about that. But without further ado, we'll have DZB talking about beyond Fermat's last theorem.
Thanks for the wonderful introduction and the invitation to speak. The slides are hyperlinked and they're available at my website, which if you just Google my initials and math, you'll find. Let me make this full screen. And yeah, so I basically just read Jackson's rec letter at their wedding for this speech. It is nice mentoring the same student for 9 or 10 years. That doesn't always or usually happen. But also, Leia was a grad student there as well. They're faculty here now, and then even some of our future grad students, like Shilpi, are their postdocs now. So it's already a nice pipeline. I'm also from South Texas, born in Beeville. Haven't been to this part of North Texas yet. Maybe the closest is Abilene, where I have some family. But it's nice to be here. So I like putting some puzzles or just fun things to do on slides. So there's one of a couple of proofs of the Pythagorean theorem that you'll see. But I want to talk about just arithmetic geometry, what the basic problems are. I find a lot of compelling examples in this area. Basic problem is to solve equations. So you have some equations, integer coefficients, say, polynomials, and you want to find integer solutions. So V for vanishing or variety is just the set of simultaneous solutions. You plug them in, you get 0, and up top you want to solve them. So crowd work. Does the first equation have any integer solutions? Does it have any real solutions? No, the left-hand side is never smaller than 1, so no solutions. The second one's pretty interesting. My most recent PhD student on a dating app was asked by the person he's now been dating for 4 years for a fun mathematical fact about himself, and he said that he was the only age which is 1 more than a perfect square and 1 less than a perfect cube. So he was 26. This is an elliptic curve, and that's an integral point on this elliptic curve, and that's the only one. So it's the only age, which is integer age, which is 1 more and 1 less, so 25 and 27. What about the third one? This one's advanced. Everybody recognize it? This is an example due to Selmer, kind of ancient, of an equation which has solutions mod every prime, has solutions over the real numbers. You can move things over and take a square root, but has no solutions over the integers or rationals, and that's actually not especially easy. So, in fact, solving Diophantine, so integer and rational equations, is hard. In fact, it's provably hard. Hilbert, at the turn of the century, the 1900s, put forth 23 problems. He gave an address enumerating many of them. It's actually pretty interesting to go read the Wikipedia page about the Hilbert's problems, because there's some controversy over which ones were well posed and which ones weren't, and therefore some controversy over which ones have been solved or not. This one was well posed. He said, devise a procedure by which, so write a computer program in C or whatever, which does the following. So it takes as input some equations with polynomial equations with integer coefficients, and output just a simple yes or no, whether there's even one solution. And if we want to solve equations, we want to be able to answer this problem. Like, forget about enumerating them all. Is there even a single solution? Well, Hilbert, this predated Turing and theoretical computer science and logic and the halting problem, and it turns out the answer is no. A computer programmed a piece of code, this is a string, this is a mathematical object that you can prove theorems about, and one theorem you can prove is that no computer program you write can solve this problem. This is not intuitive. Sometimes people might ask, well, why not just try all the solutions? 0, 0, 0, 0, 0, 1, 0, 1, 0. Well, if that finds a solution for you, that tells you the answer is yes. But, I'm going to flip back. That wouldn't work even for this first quadratic equation. There are no solutions, but that program would run forever without telling you that there are solutions. So, one of my favorite problems, I could have ended up in logic or theoretical computer science. This turns out to connect to number theory and analytic curves, but I mean, there's some cases where it's easy, like over a finite field, you can't actually try all the solutions. But even for the rationals, this is still an open problem. The kind of implication you might think over Euclidean denominators goes the wrong way. So here's an especially difficult family of equations to solve. So for Fermat's last theorem, there are some easy to spot solutions which involve zeros. P needs to be at least 3. This is easy to solve if P is 1 or 2. This was an outstanding problem. It took 300, but actually over 300 years to prove. So here's my favorite picture of Fermat with the dates, so 1665 in the solution. Here's a fun question. How many mathematicians, unique mathematicians, appear on stamps? 436. So there's a nice Sophie Germain, which has the statement of, you can prove Fermat's last theorem in the special case of Sophie Germain primes. The first stamp I ever saw was a stamp of Delene. So these slides are hyperlinked. There's a nice webpage about this. So this is Wiles. He's clearly thrilled about this proof of Fermat. The story you may have heard is to be clear, he wasn't coming out of nowhere. He was a tenured professor at Princeton and was one of the experts in the area surrounding this problem, but had an idea and had some other publications that he could kind of finish up to look productive on the one hand, but then kind of work somewhat in secret on his own. On the other hand, for 6 years, had a proof that he's talking about here. There was a gap in the proof, and his recent student, Richard Taylor, together helped him fix the gap over the year. And now, even though there is a formalization effort in Lean for the proof of Fermat's last theorem that is making rapid progress, it's widely accepted to be a more or less complete proof. This isn't just a tasteless joke. The Gap Jeans Company approached Andrew after the proof, asking him to do a jeans commercial. Outrageous. He politely declined and was not offended. He was also invited by Barbara Walters to do an interview on 2020, also declined. He does not especially like being in the spotlight, which is ironic because he now works in a building named after him. Where do mathematicians come from? I ended up starting, like Jackson, I took the proof course my second year of undergrad. But what happened that summer was I would read any kind of book around me that people would hand me, and someone in my dorm gave me this book, Fermat's Enigma, which is about Fermat's last theorem. It's a great book, but also it's really kind of more about, it's easier to write a book like this about the mathematicians than it is about the math, and it's a great book about the mathematicians. But then later, I randomly discovered some books by Ian Stewart. So Nature's Numbers, it's about 100 pages. Explains how Fibonacci numbers appear in nature. The golden ratio and spiraling. And then I went to the math library and there was a whole shelf full of books by him. My favorite being From Here to Infinity, which does the best job of any book I've seen of trying to explain what research mathematics is like to a non-mathematician. So it's kind of very different than the human side. It's what we spend inside our heads all this time doing. And then one more joke. There's some great Fermat-related stuff on The Simpsons. I mean, actually, the donut part is much more offensive to me than the Fermat part. But what's happening in the 3D one is, at the time, your these numbers are large enough to the 12th power that they would overflow your calculator, and it makes it look like that's actually a solution to the Fermat equation. Can anybody spot why that's not a solution? I don't know if you could read. Okay, so this is even, that's odd. So that one can't. So there's a great number file episode featuring Dagan Karp about this.
So is that one of your math 250 exercises?
Yeah, great. No, it was much simpler. There's some hard problems about it. Yeah, that's a pretty good one. Actually, I'm teaching it for the 15th time in the fall. So basic problem, we have some equations. The ring is a moving target, but often integer or rational solutions. And there's qualitative questions. Is there a solution at all, even one? If there is one, how many are there? Are there infinitely many? Is there some extra structure? There's quantitative. How many are there? 8 in the Fermat case. How large is the smallest solution? I'll talk a lot about that. And how can we find all the solutions? Or find them with proof? Those are two different questions. Even just finding them with confidence but without proof is not always easy. And then there's kind of moral or implicit questions. Why does some have or not solutions? Why does some have many? None. What underlying structures control this? And so kind of the easiest example to show people is Pythagorean triples. Again, here's a nice proof of the Pythagorean theorem. And this quadrant, so here are some examples. I want coprime triples, no common prime factors. There are infinitely many of these. 3, 4, 5 is a good one. And there's a geometric, there's a few ways. You can do this just with elementary number theory by thinking about prime divisors, but, well, let's flip back. If I divide by z squared, this is x over z squared, y over z squared. It's a circle, radius 1. And there's one point on the circle. If you have some other point on the circle, you can draw the line through this fixed point and your hypothetical point and intersect with the y-axis to get 0, t, some t. Okay, it's the slope of that line. It's an algebraic equation. And conversely, if I have such a t, I can draw this line and I get a point on the circle, and you can work out in terms of t what that intersection point is. So there's a back and forth, but more importantly, there's no cosines or anything involved, even though it's a circle. And you can parameterize all of the solutions. So if I clear denominators again, c is non-zero, so I can write it with one parameter. All of the solutions come from this triple. You can parameterize them. You have 3 variables before, 2 if you do it right, but there's one parameter. This is kind of example 0 in arithmetic geometry. So there's a couple cornerstones of the area. Fermat's last theorem is one. Mazur's theorem, and then there's the Mordell conjecture. So we just saw that this quadratic equation has infinitely many rational solutions. I can promote one of the exponents a bit. So if I change the x exponent to at least 5 or greater, then that fixed equation has finitely many solutions. And it has some, right? 0 plus or minus 1. But for that fixed in, there's finitely many. And there's a framework that this fits into. So for example, the shape of that equation wasn't that important. Let's make it a little better. If it's hyperelliptic, y squared equals a single polynomial, square free, means that f has no repeated factors, even over the complex numbers of degree at least 4. Then that fixed equation is finitely many solutions. So here's the framework. Oh no, Fermat curves. Fermat curves, why is Fermat's last theorem believable? Well, if you're not careful, this homogeneous equation looks like a surface. One equation, 3 variables. But you can divide by z and you get a curve. This is 2 variables. And Mordell's conjecture is really about curves and equations coming from curves. So here's an example I like. Take y squared equals this degree 6 polynomial. There's no repeated factors. I threw the negative sign in so that I can easily graph it. So on my right, this is Dan Aykroyd from the classic movie Coneheads. But this is a plot of the real points of the solution. Because of the minus, it's bounded in the plane. There are 6 roots of this polynomial, so here they are. It's symmetric. On the other hand, if you have to use your imagination a little bit, look at the complex solutions. Really that's 4-dimensional, but solve this over the complex numbers, and then wiggle it a little, and you get a 2-hole torus. This collection of real points is really like a cross-section. So this one I did in Sage, and this one by hand, really. The red lines are a cross-section of this. and you call the genus of a curve, even a curve over Q, or the integers, the number of holes you get in this complex torus. So you care about integer or rational solutions. You look over the complex numbers, you get a manifold, you count the number of holes. And the Mordell conjecture from the 1920s is that a curve with genus at least 2 has only finitely many rational solutions. So I think of this theorem or type of, well, it's a conjecture term for this slide, as the type of thing that is so interesting about arithmetic geometry. This exhibits how arithmetic, rational numbers, and solving equations is related to geometry, number of holes in some manifold. So this was really a motivating conjecture in number theory throughout the century, and it explains a lot of things. So why is Fermat's last theorem believable? Well, again, this is a curve, and then for smooth plane curves, there's a formula for the number of holes. It's not clear from this equation what that picture looks like, but there is a nice formula. And then when n is at least 4, the number of holes is at least 2. So that tells you that this fixed Fermat equation has only finitely many solutions. And of course, it's much harder to prove that as you vary over all large enough n, there's only the clear ones, but this is at least a good starting point. By the way, Fermat is actually true for 3. This is an elliptic curve, or it's a genus 1 curve. The formula gives you 1. And we were lucky. If you add equations in front of Fermat, this is our first of many ways to vary the problem. For lots of choices of A, B, and C, I forget if it's half or it's probably half, but it might be 2/3. This equation actually has infinitely many solutions. So for 3, we were just kind of lucky. 4 is really the true cutoff. I like these kind of ancient problems. Here's another fun one, the congruent number problem. A number, like 6, is congruent if there's some right triangle with integer, or we'll later allow rational, side lengths, whose area is that number. So 6 is, well, 3, 4, 5 is a right triangle, and then 6 is its area. Solving this problem gives you a curve. The quadratic is one equation, and then this isn't homogeneous for the area formula. I could put a w squared here to make it homogeneous. We've already done the divide to get a curve. So we have 2 equations, 3 variables. It's a curve. There's a formula. If you have 2 quadratics, the curve has 1 hole. So this could have infinitely many. It could not. This one has 1, at least. So the first truly interesting case is 157. If you assume $1 million worth of conjectures, so the Birchman-Swinnerton-Dyer conjecture, then that conjecture implies that this fixed equation, the congruent number curve for 157, has not just one solution, but infinitely many. It predicts, let's see, that 157 is a congruent number. Finding that is pretty difficult. So if you had to guess, how large would you guess the smallest non-zero solution? So 157 has 3 digits. How many digits do you expect?
100 digits.
100. That's pretty good. People are bolder these days, so it's 44. I had to factor this to fit it on the slide. And you definitely don't find this by brute force. There's a technique involving complex analysis that lets you do a bunch of complex integrals, and it gives you some numbers that look like rational numbers, and then you approximate them using the algorithm, and then they magically solve this equation. It was really kind of non-trivial to find it. The number of digits grows quadratically, and so the next one you would never find by brute force. But for brute force, when I made this slide in 2011, I was curious of how long it would take to find this solution via brute force. So on Emory's computers at the time, our cluster, if you check 0, 0, 0, 0, 0, 1, and so on, you could get through the numerator and denominator up to 10. So you could do 10 to the 6 many of these in about 1 minute on Emory's cluster. And so this would take 10 to the 252 years. That's a lot. But okay, according to Wikipedia at the time, there are 10 to the 9 many computers in the world. So this improves it a little bit. This is 10 to the 243. Some are a lot slower than Emory's computers, some are probably faster. That's still not that great of an improvement because the expected time until the heat death of the universe is only roughly 10 to the 100 many years. There's a couple slides where the pictures are wrong. What's wrong with this picture? Okay, no physicist. Heat death doesn't look like anything. This is
Right.
heat death wouldn't be an interesting picture. So you can add coefficients. Another way to generalize Fermat is to add variables. So this is a Fermat surface. There are still the solutions involving zeros, 1, 0, 1, 0. But actually, it's a little worse. There are lines on this surface. I can set x equal to z and y equal to w, even make them coprime, and that gives infinitely many solutions. But the set of known solutions is codimension 1. So it's a surface, but there's some easy to identify curves, in this case lines on the surface, with all the rational points. So the conjecture for Fermat surfaces is that these easy to spot solutions are all of them. And we've made zero progress. That's the problem. We've tried nothing and we're all out of ideas. The cutoff is 5 instead of 4. Fermat's last theorem with 3 variables has this rich history of Gauss and Euler and everybody solving particular cases, or Sophie Germain. If the prime has a special form, then you can solve Fermat's last theorem, or if it's an irregular prime. There's not a single exponent greater than or equal to 5 where we can prove that that fixed equation has only the obvious solutions. One advanced comment, in terms of algebraic topology, one difference is that curves of genus at least 2 have large non-abelian fundamental groups. Hypersurfaces of dimension at least 2 have trivial fundamental groups. So a lot of the geometry in the background just is 0 or empty to start. Still, n equals 1 is easy, n equals 2, the same intersect with the line trick works. N equals 3 is pretty interesting. If you know some algebraic geometry, that's a cubic surface. There's a description of it as you blow up the plane at 6 points. There are 27 lines on it, but you can parameterize them non-trivially. For 4, this is what's called a K3. It's one of these nebulous intermediate cases. And K3 surfaces are special in a lot of ways. There are actually, unlike the 3-variable case, a bunch of solutions when n is 4. Noam Elkies found a rank 1 elliptic curve on it. So there's a new curve that isn't a line. It's kind of complicated, but then for 5 and further, like we've checked for other curves on this, I'll show you later. There's a lot of experimental data, and we've really made 0 progress. And just to highlight how interesting the Porte case is, here's a twist of that. So I already dehomogenized for you, and there's 2 coefficients. When I started graduate school, Bjorn Poonen, my advisor, had this listed as one of the problems on his webpage. And the conjecture, the relevant quote, to Swinnerton-Dyer, was that the visible solutions are it. There's some solutions involving zeros, and those are all of the solutions. This was, again, kind of spectacularly wrong. Unlike the congruent number 157 problem, there are 7 digits in the numerator and denominators. This one was not found by some fancy method, well, it's still fancy, in that there's a pair of mathematicians, but who do computer science in Germany, Eisenhower and Janel, who, there's a trick. You can separate the variables of this equation into some on the left and some on the right, and if you try brute force, there are some kind of optimizations that are very special that they could do. They found this. Swinnerton-Dyer, who's passed away now, but at the time would not tell us why he thought those were the only solutions. He said it wasn't just optimism, but and other people like Ronald Van Wyk have some ideas in terms of poles of zeta functions for why they're actually, we should have known there were infinitely many. If you did the back of the envelope calculation, 0, 0, 0, it would take 10 to the 16 years to find this. The age of the universe is roughly 10 to the 10 by some estimations. We'll probably never find the next one. One more gargantuan number type problem is sums of cubes. This was in the news recently. It is an ancient problem, but now we've already dehomogenized. This is legitimately a surface, and you want to know for which n can you represent n as a sum of 3 cubes. You can always do sum of 9 cubes. That's like for squares, that's Lagrange's theorem, so it's sum of 4 squares, 9 cubes. It's the Warring problem. Some of these are easy. 6, okay, so 4 and 5, actually 4 and 5 mod 9. If you look mod 9 and compute what the cubes are mod 9, you see that there are no sum of cubes mod 9 that is 4 or 5. And so the optimistic conjecture due to Heath-Brown is that the converse is true. So if this equation, if n is not 4 or 5 mod 9, then this fixed equation for that fixed n has an integer solution. Now, I don't know how confident Heath-Brown is. I'm not that confident. Maybe I'm above 50% on this, but I don't have a great conceptual reason why these should have solutions. And then it's difficult to collect data. So for these, okay, 6 is the first one where it's kind of not immediately clear. I mean, if there's a 2 involved, what the solution is. Of course, sometimes there's more than one solution. What makes brute force difficult is that you're allowed to use negative numbers. If this were a sum of even powers, then there's finitely many things to check. So it was just an interesting computational number theory problem recently solved by Booker-Sutherland. Again, the slides are hyperlinked. I really recommend this Quanta article. So okay, so 32, mod 9, it doesn't work. 33, they found a solution. Here it is. This is an incredible paper. They make, I mean, if you like computational things, they just have lots of ideas about how to optimize these computations. And then you can try to take more data. 42 is a good number, so they put the 42 on it. If you want a hoodie with 42 and some math, they have a good one. And then the next unknown, so there's another one for 3 that they found. 144 is the next one where there should be a solution, but we haven't found them yet.
114.
Or 114, sorry. Thank you. I'll talk a lot now about generalized Fermat equations. So there are a lot of ways to generalize Fermat equations, but usually when people say generalized, what they mean is that you vary the exponents. It's no longer homogeneous. It's genuinely a surface, or a priori, and not a curve. And I'll explain in a lot of detail why exponents 2, 3, 7 are special and interesting, but when I started grad school, the first Monday, T, I went to T, and Poonen was there, and I thought I might want to do number theory, and so I tried to find an excuse to talk to Poonen. But when you're 21 or 22, you're awkward, and some mathematicians, continue to be awkward. And so I talked to Bjorn, and I asked him, how to introduce myself, and then how did you win the Putnam 4 times? He was a 4-time Putnam fellow, and he's like, oh, I don't know, and then explains to me that, well, he worked all of the previous Putnams before he took it the first time. And at first I was unimpressed by this, and I was like, oh, well, I would have been a Putnam fellow if I did that. And I was like, well, why didn't I do that? Actually, that sounds kind of hard to do, and now I'm still unimpressed. And then, okay, but then I figured out, it's easy to talk to mathematicians. You just ask them, what did you recently finish up? What have you been thinking about lately or working on? So I asked him, what have you been working on lately? And this was the paper he finished. So they just submitted this for publication that week. It was a 51-page paper that's computational, but got accepted into Duke Math Journal, which by some accounts is maybe the number 4 plus or minus math journal. The first time I heard another mathematician unironically describe someone else's work as a tour de force. And it was about this single Fermat equation and solving it. So 51 pages. There's the ones with zeros. There's the Catalan solution. So 7's not involved. If you put any p here, x squared plus y cubed equals 1, this works. Okay, that when you put a 1 for z, that's resolved. But then there's another one. That's not too bad. You're allowed a little bit of noise. And then I think people thought these were all of them until in the 90s with better computers, there's some with big digits. And actually, even when I give students to teach them magma, I give them some problems like, I just tell them this equation has 16 coprime solutions, find them all, and if you try 0, 0, 0, 1, 0, 0, you won't find these. But there's a trick. You plug in for y and z, and then you check whether it's a square. Then it runs overnight on your laptop and finds them. Maybe his most famous theorem, whenever this gets posted on Reddit or Imager, the top comment is always, that's not a valid proof, maybe he has a small fist. And that's actually the case. So he was born missing one of the joints in his the right hand. Again, very clearly.
So this is all by Chabot or something?
Oh, well, and much more. So yeah, I'll say a bit about the method. So first of all, it's really the modular method, like in Weyl's proof of Fermat, except that instead of no modular forms, you get 14. And so there are some twists of x of 7, the Klein-Quartic, that you have to do Chabot on. Except to do Chabot, you have to figure out how to do descent and compute the rank of the Jacobian on the Klein-Quartic. So they just invented a technique that works specifically for twists of the Klein-Quartic for computing ranks of Jacobians. And then all of the ranks but one are in the Chabot range, and there's one with rank 3, and ask me more about that at the end. So they actually had a moment where they thought, we put in all this work and all for naught. And then had to find like a new technique involving clever Mordell babysitting to handle it.
Is that Ed Schaefer?
Ed Schaefer, yeah, who just retired recently. Yeah, and who had a lot of the early papers in the 90s about computing ranks and making a computation. Yeah, he was great. My office mate did cryptography, and Ed, even though he was at Santa Clara, advised my office mates. They actually got to see him a lot. So the general problem, why is 2-3 special? So generally, what are the solutions to a plus b to this equation? Well, first of all, even though it's a surface and not a curve, there's a stacking curve. There's an exotic geometric object which controls it, and there's a theorem in the mid-90s due to Darmani-Granville, which is kind of like I was saying with Fermat and Mordell, that so for fixed A, B, and C, at least 2, this equation has finitely many co-prime integer solutions if and only if this quantity chi with denominators is less than or equal to 0. So just to check, 2, 2, 2 has infinitely many. 2, 2, 2, this is positive. It's 1/2 on the left. 4, 4, 4, you get minus a quarter on the left. That has finitely many. So the quantity chi evokes the notion of Euler characteristic from topology, but there are denominators. I'll just say, without any further comment until questions, that you can scale solutions, but the scaling is weighted. If you scale a solution by lambda, you have to scale x by lambda to the BC, y by lambda to the AC. It's a weighted action. And when you take the quotient, you do get a curve, but really you want to work with what's called an orbifold, where there are some fractional points there. And then what Darmani-Granville did, even though they didn't use the word stack or overfold, is prove the Mordell conjecture for these exotic curves. So again, this is the analog of applying the Mordell conjecture to the Fermat curves. So there are some sporadic but finitely many solutions, and I've highlighted in red and blue the 2s and 3s. So you'll notice every known solution to this equation where this quantity is in the hyperbolic winning range involves at least a 2 or a 3. But there are some. There are some exponents of 8, 7, a 4, and a 5. And this is it. As I'll explain in a second, we've done some extensive computational searching and only found these. So these are all of the solutions, such that this quantity chi is negative. My understanding is that this department knows who Andy Neal is, but he was a wealthy banker and math enthusiast who cares a lot about this problem. And in fact,
He's still a wealthy banker.
that's true. That's right. I used to think a lot about this problem. I still do, but I also used to. And offered, actually, initially it was a $5,000 prize for a proof of the conjecture. And then I think he was a little too optimistic. I love his optimism. So he's like, okay, I'll offer an extra $5,000 per year until it hits $50,000. Okay, and then it hit $50,000, and eventually, this was in the 90s, and then the Clay Millennium Problems were posed, and those were $1 million. So first he bumped it up to $100,000, and then eventually went for a full $1 million. Or even for a counterexample, but the amount of prize money you get for a counterexample depends on the size of the counterexample. Depends on pi. And I guess he would have liked me because I had spent a lot of time thinking about this, and I also spent a lot of time trying to convince my best friend, who's a mathematician, to work on this problem with me. And he convinced me that my return on investment for any time I spent working was much better just trying to get tenure than trying to split this prize with them.
Yeah.
Yeah. There's extensive evidence for these problems though. So I had dial-up internet in the 90s, and some such people might remember this SETI at home problem where when you were not using your computer, but it was connected to the internet, you could use the spare cycles on your computer to help search for extraterrestrial life. This is a real thing we did in the 90s. Didn't find any. But then there was a better project that came along, the ABC at home project. So the equation A plus B equals C, you're not necessarily looking for perfect powers, but you're looking for things which are close to perfect power solutions or highly divisible. And there was a distributed computing project to search for counterexamples to these kind of problems, or at least things that are close to counterexamples. And that's fun. When I discovered this, I immediately went and found the data file, which is, at the time, this seemed gargantuan, 2/3 of a gigabyte. And that was only keeping track of A and B, because if you have A and B, you can deduce C from the file. And that's where I realized you can't just open a half a gig file in a normal text editor. You have to use a terminal to process it. It just crashes your computer. So why is 237 so interesting? This is 42 again. It's as close, so 237 makes this quantity chi as close to 0 from below. Remember, we want it to be negative as possible. 236 will give us exactly 0. So it's in the medium range. 235 we'll see as infinitely many. And then if you vary, anyway, it's a fun elementary number theory problem. But then why would being so close, so first of all, it counts. It's in that range. Second, there are actually a bunch of large solutions. And there's kind of a probabilistic heuristic for, in general, why this should, overall exponents have finitely many solutions involving, you make an assumption that's not really true, that when you have polynomials, the outputs are somewhat randomly distributed. Any kind of weak assumption you make like this implies that there should be finitely many solutions. There's no way to make that precise. But then, for these heuristics to work, you need this quantity chi to be small. So there is some sense in which the heuristics which predict finitely many break down or only barely work when this quantity is slightly larger. So somehow 237, there's a reason that it has solutions. But some other fun ones, more or less right after the proof by Wiles, Teller, etc. of Fermat's last theorem, Dorman and Morel took the modular method that they used in the proof, and then first just tried to get some low-hanging fruit, tried to apply it to other problems. So this one's not any harder than Fermat's last theorem. The exponent's n(n)2. This quantity, okay, we do arithmetic. Okay, if n is at least 4, this is less than 2/4. Okay, great, which is it? So if n is greater than 4, this quantity chi is negative. And then they prove that as you range over all exponents n, at least 4, this equation has no non-trivial solutions. And it's basically the same method. If you know about Fermat, when you get to the end, there's not any interesting modular forms. But we were talking about REUs earlier. And okay, the first one's not an REU problem. These methods are, it was an Annals paper. But notice 2006, and Zizek is really a Chebuti person. Some of these others are like linear forms and logs person, some transcendental number theory that's too hard for me. And it's an ancient problem. So if you look at the Fibonacci sequence, here's the first several terms. The highlighted ones are the only, or the only known perfect power. So 1's a perfect power, 8 is a cube, 144 is 12 squared. If you keep going, you don't find any other perfect powers. So I forgot to check how far back this problem goes, but people could prove, like for Fermat, people could prove these were the only squares in this sequence, and these are the only cubes. One thing that makes it difficult, like Fermat, is you do have some perfect powers that propagate. But again, it turns out there's a non-transparent way to apply the Frey curve, Wiles' method to this, and so they proved. And by the way, it must be non-trivial because it took another 10 years after the proof of Fermat, but there it is. And then I helped run an RU for a long time. I gave a pair of exceptional RU students this problem. I mean, these are not normal students. Isabel is tenured at Brown now and has more publications than I do in better journals. And so we had them look at other linear recurrence relations, like Lucas sequences. I mean, that one's fun because the solution is 2 to the n minus 1. And okay, you can't handle every Lucas sequence at the same time. They were able to take a big swath of them and say as much as you can say using Lyell's method. And then the kind of neat thing about these type of problems, like even the Dormant-Morel theorem from the previous slide, is that when you try to plug these problems into existing techniques, you get asked back some other interesting problem about Galois representations or abelian varieties. And so one thing they did in this paper is kind of spell out a bunch of problems that we don't know how to solve about abelian varieties and modular forms. Anyway, not a normal argue pair. The converse case is extremely interesting to me too. So when the exponents are 2, 3, and 5, this is a case where this quantity chi is positive. So this predicts that there are infinitely many solutions. In fact, you can parameterize them. So infinitely many solutions, you can parameterize them. Here's how you do it. Here's a degree 12 polynomial in 2 variables. If you know a lot of number theory, that's related to the coordinates of the cusps on the modular curve x of 5. But anyway, it's just fairly, you can look at it, it's a polynomial. H is the Hessian. This is the thing from multivariable calculus where you take the matrix of mixed partial derivatives and its determinant. The Hessian is like an invariant or a co-invariant of something. And there's a similar degree 3. This is degree 2. Degree, another type of thing with mixed partials you can compute that won't fit on the slide. But it's just, in MAGA, you type this one in, and then you take derivatives. It's linear time. And then you plug these in, you divide by some 2s and 3s to make the things coprime. And then these 3 polynomials solve as polynomials this equation. It's kind of majestic, I don't know, the first time you do this, because especially that t, it's just a giant mess. And then you plug these in to this non-homogeneous equation, and there's lots of cancellation, you get 0. And so then if you take integers s and t, which are coprime, and plug them into f, h, and t, this then gives you a solution, or infinitely many, to this. Now, why are there so many names attached to this theorem? I would really like to know, and this is unknowable, what math Klein actually understood beyond what he wrote down. But he spent a lot of time essentially working out the invariant, or the representation theory and invariant theory of the dodecahedron. And that turns out to be related to this problem. Zage and Boykers figured out that not every solution comes from this particular f. It's not as clean as Pythagorean triples. There's 27 different f's, which are homogeneous degree 12 equations, such that when you take its Hessian and this degree 3 thing and plug them in, it solves it. And then conversely, every solution to this comes from one of these 27f by specializing. If you like stacks, these are Étale covers of that stack from the book. That's a side comment. So it's really kind of and this was, so Edwards was a PhD student of Boykers. This was his PhD. It's really kind of a work of art. And this one we're pretty sure is correct. The other people made, like it's a lot. So, like I said, I've thought a lot about this. There is an excellent paper by Dormant called Faultings plus epsilon. So Faultings is the proof of the Mordell conjecture. And what he does is thinks very geometrically about why the proof of Fermat's last theorem works and where this kind of mysterious Frey curve comes from, and realizes, okay, it's related to algebraic topology and which covering groups or triangle groups, that kind of thing, or rather correspond to modular groups. And laid out kind of a blueprint for several decades of work where he said, so we haven't solved one, but there's a much larger slide saved in this, a table rather, and says here are all of the collections of exponents where Lyell's ideas in the proof of Fermat's last theorem might help us solve these Fermat equations. So I can't really say codimension 2. It's not, it's infinitely many, but then it's not close to all of them. And over time, people have, in each of these asks you some interesting new question about representations or geometry, and people one by one solve them. And so after I passed my oral exams in grad school, I went back to Bjorn with the 237 paper and said, I want to read and understand this paper. And then we read it, and after a while understood it, and I was like, well, what's the next thing to do? 2, 3, 8, and 9 had been done. Those are easier because 8 and 9 are not prime. You can reduce to 4 and 3. And so I worked on the 2, 3, 11 equation. I didn't solve it. But the idea I had for the 2, 3, 11 equation, I eventually gave up, and then much later realized in grad school that the same idea works for the 2, 3, 10 equation. So my first theorem, as a student, published in IMRN back when it was easier to take papers into that journal, was solving just the 2, 3, 10 equation. And then once I gave up on 11, I gave everything I'd written up to the steamrollers, Mikhail Scholl and the experts, and they were able to do 2, 3, 11. So there's actually a much larger slide than this, not that much larger I could make, but that's a nice point. And then I want to talk about one more theorem. So this is Falting's and Mordell again. Again, Falting's, Voida, Bombieri gave some independent proofs. You have a curve of genus at least 2. The number of solutions over Q, that's what that notation means, is at most infinity. So again, there's this hyperelliptic case, this finitely many rational solutions. And you can ask about the higher dimensional generalization. Instead of a curve where there's finitely many points, if you have a variety of general type, if you like curvature, these are negatively curved varieties, then the rational points are not dense. And so with like these Fermat surfaces, you should think of, you have a surface and there's some finite collection of lines or maybe curves, all of the solutions live there, and then the complement has no solutions over Q. So again, this isn't quite, we've tried nothing and we're all out of ideas, but while there's progress by people in this room, I would also say we're not that close to a proof of this. Some really new ideas are needed. And one of my favorite problems is, okay, well, if you can't solve a problem, ask a harder question. Given some collection of equations, that's what X represents, maybe a curve, compute the number of solutions exactly. Okay, if that's too hard, at least try to compute some upper bounds on the number of solutions. And so my favorite conjecture, which actually is almost, but still not quite known yet, is the uniformity conjecture. So it's kind of ridiculous. There's a constant which depends only on the genus, the number of holes of the curve, such that as you vary over all curves of that genus, there's a uniform upper bound. So maybe the upper bound is 600 for G is 2. Okay, that won't work. 700. Every curve with genus 2 holes, has at most 700 solutions. Now, this was not a widely believed conjecture. In fact, it kind of sounds ridiculous, but then there's a famous theorem of Capra-Sagaras-Mazur, which is Lang's conjecture. So the higher dimensional conjecture, similar to Mordell, implies this uniformity conjecture. You can set this problem up as a moduli space, and okay, what's neat is, initially, this was not taken as evidence for the uniformity conjecture. This was taken as evidence against Lang's conjecture, because they thought this uniformity one was so ridiculous. And the apocryphal story that
Well,
I think,
that was Mazur's view. It's Capra and Harris, it's less clear, but yeah.
Yeah, exactly. Well, I mean, but yeah, but still, then, oh wait, wrong way. Then what happened is people spent maybe, what I hear is about a month at Harvard frantically trying to write down examples of curves with more and more and more and more points. And so here's kind of a table of the best. I'll show you the genus 2 one. In general, for genus G, you have a linear lower bound, meaning as you increase the degree of your polynomial that you're trying to solve, you can force it to have more and more solutions, but kind of asymptotically, we still can't do better than linear in the genus. But the genus 2 case is kind of an outlier. Nomokis, who else found it? I mean, here's the equation. It's a needle in a haystack. If you kind of tweak the coefficients even a little bit, then there are no solutions. But this particular one has 642 solutions. Just here's the representative one. There's some neat tricks for this. But then, yeah, you change the coefficients even a little bit, and there's 0. So I'll finish by saying another theorem I'm very proud of is at least when the rank is low. So here's what I mean. You have a curve that has genus G. There's a abelian group you can attach to your curve that tells you a lot about it. It's finitely generated, so it has some free part and some non-free part. And R is the rank of the free part, the number of copies of Z. If that's small, that number's R, small meaning most G minus 2. So if you write down a random curve, this number R is usually 0 or 1. There's some theorems like that. But it can be greater than G minus 2. Then we have this uniform upper bound on the number of points. As G grows, I mean, this is quadratic, the lower bound was linear. This upper bound, it's definitely not the truth. The expectation now is the upper bound should be also a linear polynomial in G. We're getting closer. And kind of the tools we use to prove this are some ideas due to Coleman, where you can generalize a lot of analysis, even Banach spaces and stuff like that, to the p-adic setting. That's from the 80s. And then the later stuff is, the modern approach to Berkovich is, okay, Berkovich spaces, he didn't call them that, but analytic spaces, but where there's these kind of fractal-like p-adic manifolds rather than complex manifolds. And so here's to finish just a picture of one of these and kind of the ideas of the proof for that. I mean, this looks like an exotic object, but it's actually fairly concrete. You can write down integrals and functions and do analysis and harmonic analysis on these. And there's a way to write down certain functions on a space like this, which have finitely many zeros, but vanish exactly on these rational solutions we started with. And then a way to actually analyze using combinatorics and analysis. So thanks for your attention. That's it.
Any questions?
I think there's real recent work that gives an upper bound exponential of the rank for general rank.
Yeah, if I hadn't spent much time talking to Jackson today, I would have added a slide. On our group chat, somebody else asked about that paper due to Shinny Yuan and others, and my reaction was there needs to be a better journal than Annals for this paper. It's like 170 pages. So they give if I go back, there's a conjecture due to Mazur that there should be an upper bound on this quantity, which is a function of R and G. And there's some belief now that for elliptic curves, that this rank is bounded, in which case you would get a uniform upper bound. I don't think there's as strong of an expectation either way that ranks of Jacobians are bounded, but if they were, that would give you a uniform upper bound. And the novelty of that paper is they give extremely nice looking constants in an expression. And so in fact,
That's still exponential in the rank.
it is, but yeah. And then that's not just an outlier paper. I mean, Shinny Yuan and others wrote a series of papers that are all these gargantuan, 200 to 300 page papers building up the theory they needed for this. And, yeah. Although that wasn't a question. Yeah.
But the real question related to the rank thing is you can also make a stronger uniform conjecture from Caparrós, Harris, and Mazur, and the analog for ranks of that is there an upper bound on the rank that holds for all number fields with finitely many exceptions for each number field?
Yeah.
So that's the real question.
Yeah, the strong version. I don't have the strong version in these slides, but I do have it in the survey. But, yeah.
Are there any other comments for David? Okay, well, if not, let's thank you again.